Hello everyone. Welcome to the course on Introduction to Computer Systems Design as a part of the Systems curriculum in BS in Data Science. And this is a course which is going to be focused on designing of computer systems and more of the design philosophies that is going to be used as a prelude to more advanced system courses like computer architecture or operating systems and so on. And again, this is going to be a 12-week course and is going to span a broad set of design components. We are going to focus mostly on the building blocks of a modern computer system, particularly digital logic and introduction to computer organization, how CPUs work, how programs are executed on a CPU in a little bit more detailed manner about the hardware of the system. Okay, so let us analyze the title of the course, which is Introduction to Computer Systems Design, right? So there are several things to note down here. The first one is computer systems, right? So what do we mean by computer systems? Typically, we are all used to seeing regular desktop computers, PCs, laptops, or servers as computer systems, but there is a broader meaning to that. Even your smartphone that you are using is actually as computer systems, and that entails a wide variety of systems that we see around, and we can label them as computer systems. We are going to look into them, and we are going to look into the design principles of these computer systems, because at the heart of a computing system or a computer system, we do have this processing units that we typically refer to as CPUs and so on, or even there are other peripheral circuitry that is there. What are the design principles? What are the recipes that are actually followed in order to build such systems, right? So that is the meaning of the word design. We are going to go into deeper discussion of the design principles, and this is an introductory course, so we are going to be somewhat restrictive, because computer systems, as we see today, is continuously evolving and complex. We are going into we'll look into a few examples and kind of understand that how complex systems can be, right? And we cannot really keep track of the entire array of this evolution, right? The entire timeline of this evolution. So this is continuously going to evolve, and it is going to be more and more complex. What we will stick to are what are the fundamental principles of this design, right? And one more thing I want you guys to remember is that we are talking about, when we talk about computer systems, we are essentially talking about digital computer systems, right? We are going to clarify this term digital in the course of today's lecture, and this is important to remember that there is a fundamental difference in between analog and digital. In the digital world, we typically deal with discrete data, which is often represented in terms of bits 1 or 0, you may have already heard, and that is why we can develop the digital logic on top of this digital information, right? So all the logical circuitry that we are going to develop on top of this information, which is digital, that will be digital logic. Okay, so hope you have kind of a good idea about the name of the course at least. So this will be Introduction to Computer Systems Design. Okay, so now given that we have to understand, or at least kind of calibrate ourselves with what computer systems are, we will start with some examples. Okay, so modern computing systems, as we see around, there's an array of various computers around us in action, and I have put some pictures of these computers that we always see around us in various shapes and forms, right? And they are all heterogeneous devices. They are not really all the same, and I have deliberately not included desktop PC that you are already aware of, or a laptop, right? But apart from that class of computer, you have this vast diversity in computing systems world, starting from something as your smartwatch, all right, a smartwatch many of you might be using. So this is a smartwatch, smart watch to a mobile handset, right, or like a smartphone to something like a smart thermometer to even a more rudimentary example like a washing machine, right? And then you have all these modern gadgets like this robots, right? This is a robot from Boston Dynamics, and many of you might be aware of the different feats, that many complicated feats these robots actually perform. So these are robots, right? And of course you have things like drones, and these are all automated speech voice recognition systems, personal assistants, right? So these are the things like Amazon Echo Dots, Alexa, and so on, right, to something as complicated as a self-driving car. So you may ask that, okay, all of these are computing systems, but what varies across these computing systems are the amount of resources that are there in these computing systems, as well as the kind of tasks they perform. So you can see that some of the tasks that a washing machine performs is fairly simple, right, compared to what a self-driving car or a smartwatch can do. Okay, so a washing machine may be having a fixed set of tasks to do. It could wash for some time, draw water, drain out water, dry it up, right? And often we call it pre-programmed, right? So it is a simple array of like set of instructions that is going to be executed by the computer which is residing inside the washing machine, right? For example, you can also take the case of a microwave oven, which also has a series of instructions. For example, you want to heat milk, or you want to heat curry, and so on. So based on that, it will adjust the time it wants to heat the thing, how much power it is going to use, and so on. Similarly, if you look into a drone, it has a computer inside which is going to make sure that the drone has a stable flight, right? For a drone, the computer, I am putting it in quotes, computer ensures a stable flight. And how does it ensure a stable flight? By digesting information from a lot of sensors. For example, pressure sensor, altitude sensor, inertial sensor that measures acceleration, and so on. And using this sensory data, the computer has to decide how much power it wants to put in one of these or all of these propellers, right? How much thrust it has to put, and based on that the drone will be able to balance itself in the air. If you look at the Amazon Echo Dot example, or this Alexa kind of devices, human beings are going to be sending some voice commands, right? And this device is going to interpret that speech into some digital form. It is going to make sense out of it, and then do whatever it was asked to do. For that, you have a computer that interprets human speech, right? So you have a computer interpreting speech, rather human speech. Okay, and I don't have to tell you about smartphones. It can do many sorts of work which are more complicated, or kind of encompassing many of the computing specialized computing devices that you see. For example, Alexa, or a smart thermometer, and things like that. So it can take pictures, it can stream high definition videos, you can play games, even you can record, edit videos, and so on, right? So these are mostly very computing intensive tasks that these gadgets are able to do, right? And of course, a very complicated example is a self-driving car, which is a mammoth computing system often because it has an array of sensors around it. So you will see typically this kind of cars are filled with sensors, and lot of sensory data is accumulated in a computer that is residing inside the self-driving car. It has to process all this data and decide how to maneuver obstacles or how to have a safe and stable uh, journey across the road, right, without causing any accidents and so on. So if you see, all of these are computing systems, and all of them has some commonalities in between them, and that is they are having an internal digital computer or a processor which is going to execute a set of instructions or execute programs. Okay, so hope you have a feel of how modern computing systems look like and their spectrum of the different tasks they can do. Okay, so we should not be restricted to think that computing systems just as server class computers or desktops or laptops. That is much more than that, and this gives you a feel of how computing systems are, or how, what they mean and what they look like. Okay, so here I show you an timeline for the evolution of a cell phone handset. This will also introduce you to how things have evolved, because in the first slide, if you remember, I spoke about it is evolving and complex, right? So if you look into this picture, on the right hand side I show a Google Pixel 7 device, which is one of the latest smartphones in the market, which is sold in 2023, and compare that with a Nokia 3310 handset which was available in the market in early 2000s or late 1990s probably. So both of them are computing devices. They, you can use them to make a phone call, of course, but Google Pixel 7 as a modern smartphone that has a lot of compute power compared to what you had in an old Nokia phone. Okay, so what happened over the years from this 1980s to 2020s, the systemic complexity of the systems has increased. Okay, the internal circuit, the architecture of the CPU that is inside the central processing unit, or the processor of the computing system that is inside, has increased its complexity. So it can execute a lot of complex tasks that an old phone in this particular example would not have been able to do. For example, the Google Pixel 7 can do things like face recognition, right, or augmented reality, virtual reality. All of you have come across these terms. Whereas a Nokia 3310 phone, it is unthinkable of, right? You cannot do something which is even a more complicated game. You cannot play on that device. Very simple games probably you can play. So what I wanted to say is the systemic complexity does increase. It is evolving always. Even in maybe the next 10 years, phones are going to be much more complex, and much more compute power is going to be packed in the phones. Already a lot of machine learning, deep learning are being, inferencing tasks are being done on these phones, but which was not a possibility 10 or 20 years ago. Okay, so even down the line it is going to become more and more complex, but what we are going to focus as a part of this course is what did not change, or what are the fundamentals that somebody has to keep in mind in order to design such systems. Of course there are additional uh, technologies or additional things that somebody needs to learn, but there are certain things that has never changed, right? So how you design such circuits from the get go is going to be the focus of this course. So I'm going to go into details, but before that, we what we want to say is that we have to be clear about the fundamentals of this design, especially the basics, right? What entails a design, or I would say, what are the Lego blocks that you can put together in order to build a complete system. What are the past and present dominant paradigms? So there are certain trends that people followed maybe in the late 80s versus mid 90s versus current day. So you want to kind of understand the past and present dominant paradigms, and of course along with it we want to understand the trade-offs, right? When we try any design, you want to kind of understand what are the various trade-offs that are associated with those designs. What are the shortcomings, what are the advantages of a certain design? Some circuits are large, some circuits are small, some circuits are more power hungry, some circuits are less power hungry, right? So you want to kind of understand the pros and cons of these various designs which are going to achieve the same job, right? As an example, I can tell you that you can design a very simple computer that can add numbers, right? It's a very simple computer that will be able to add two numbers. You give a and b, it is going to, the hardware is going to output a plus b, and the same circuit can be designed in multiple ways. Okay, so some circuits are going to be more complex, but it will be maybe more power efficient or maybe more fast compared to a simple circuit, right? We are going to look into those specific examples, but that is going to kind of introduce you to these design space trade-offs. And again, there will be certain things that did not change across these adders. The fact that you need to add, and what's the logical functionality that lets you add to numbers, or rather add to bits. We are going to go into the details. And of course, there are some techniques which I prefer to call recipes, right? It's very much like cooking, right? If you need to know a certain set of recipes in order to solve these design problems. When somebody poses you with a problem and asks you to design the circuit or design the system for that, you should be aware of some techniques that you should be utilizing in order to design them. Okay, so this is the background. We are going into the details of uh, a little bit more details of what this course is going to entail. So this is basically a background of the uh, computing systems. Okay. So regarding the textbook, we are going to follow this book by M. Morris Mano. This is pretty much a standard textbook that is used for introducing computer system design and computer organization to some extent. So this is going to be the reference, main reference book, and there is an additional reference if you feel more interested in looking up certain aspects. You are welcome to use this textbook. So that is only for your advanced reference. So this is an advanced book. This goes into more details into computer architecture, and even for organization or digital design, it is going to explore things in a much more in-depth way, right? So some of the background that is required to understand all the details in this book are not going to be covered in this course, but again, you are if you feel any doubt, you are welcome to ask our questions, or just refer back to the instructions and so on. We are going to help you if you want to understand any specific portion or specific problem that has been discussed in this book. Okay, but typically this will be an advanced reference. The basic textbook is going to be the Digital Logic and Computer Design by Morris Mano. Okay. Next is we have understood from a very superficial level what computing systems are, and now we are going to see into a little bit of more details of the individual blocks that are there. So in a computer system, you typically have these three units. One is the computing unit, which is typically called a processing unit or a processor or a CPU or a central processing unit. There are many names that are going to be associated with this particular unit. I can call it a processor or a processing unit or a central processing unit. Often you have all come across this term CPU. That is a unit that actually is going to process data. Okay, so this is, I would say, data processing. Then you need to have a place where you want to have the data stored, before computation you want to read the data from that store, and after your computation has been done you want to save the results, right, save the processed data. So this is called a storage unit. So this is for data storage. And there are variations in terminology. Some are permanent storage, some are temporary storage. Permanent storages are where you typically store data for a longer period of time. Often it doesn't need power to save that or to store the data, to maintain the stored data. Whereas memory subsystems, there are within the system there are temporary storage places where the CPU directly interacts with them. So there are various levels of such memory systems, and we are going to look into this when we study what entails a memory system. There are registers where data is stored temporarily in the CPU and so on. So or RAM, for example, you have all come across random access memory RAMs. Whereas storage system is more like a hard disk, where even if your computer is turned off, the storage system or your hard disk is not going to lose the content that has been stored. Okay, so there are vast varieties of such storage units, and we are not going to go into like too much of details of this, right? Rather, we are going to get a high level idea about all these different units. Then you have a communication unit, because you need some communication to read the data from the storage to the computing unit. Often this flow of data from the storage unit to the computing unit is called a read operation. Whereas when you try to process the data and store it back, this is called a write operation. So you need to have a communication unit that is able to read and read from the storage unit and write back to the storage unit. Often you want to also have a communication system that can communicate in between multiple computing systems, maybe using a network or some kind of a bus that is going to be used for ferrying the data across storage units or across computing units. So that is also possible. And this logical partition of a computing system into these blocks was done by von Neumann in one of the seminal works. You are all interested. If you are interested, you are all encouraged to look up this particular piece of article, which was one of the pioneering works which defined how computer system block should look like. And this is what we have realized today, right? All of the computing systems today typically have these three blocks. Okay, so preliminary discussion of the logical design of an electronic computing instrument. So maybe the word computer was not very prevalent in the 1940s, so they call it an electronic computing instrument. So it will give you you don't have to read end to end, but you can just skim through what they wanted to say, and what I said as a part of the block diagram above is an essence of what has been said there.